Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. And in today's session, we're going to be streaming live on YouTube as well as being on Zoom. And what are we going to be looking at? We're going to be looking at some practical organic chemistry. Specifically, we're going to be looking at the synthesis of an organic solid, the purification of said solid, and how to check for the purity of our newly synthesized organic purification of said solid, and how to check for the purity of our okay, sorry for the feedback there, now that we've sorted out that technical issue. So we will be looking at, as I said, how to check for the purity of that organic solid using different types of melting point apparatus. As usual, if you've got any questions for me during the session, please feel free to use the chat box in YouTube or in Zoom, and I will be stopping intermittently to answer those questions for you. And towards the end of the session, we will look at some actual exam questions, looking at different aspects of practical technique relevant to the synthesis and purification of organic solids. Okay, so if you can give me a few seconds while I link my tablet to the session, we will get going. Brilliant. So yeah, we're back and ready to go. Practical chemistry, synthesis of an organic solid. And at A level, typically there is one particular synthesis that most students will encounter, whatever board you're doing. And this is, of course, the synthesis of aspirin. So let's start with the synthesis of aspirin. And like with any other organic synthesis, there are essentially three key parts. The first is the preparation, in other words, mixing your reactants and reagents together. Second part would be to separate out your newly formed product, often called the crude product. And then in the final part, carrying out the appropriate purification to get your pure product out. Okay, so we're looking at the synthesis of aspirin. Now, what is aspirin and where does it come from? So if I zoom into the detailed prep, you can see there in the top left-hand corner your balanced equation, and that reactant there is benzoic acid. So 2-hydroxybenzoic acid, to give it its full name, because you do have a hydroxyl group at that 2 position. So we've got 2-hydroxybenzoic acid, and we're going to be reacting it with ethanoic anhydride. So ethanoic anhydride is an example of an acid anhydride. And what are we doing? We are effectively acylating this hydroxyl group, the OH group. So when we do acylate it, there we go, you've got your product, aspirin. So we've taken the OH group at the 2 position and we've acylated it using ethanoic anhydride. A byproduct of this reaction, a byproduct of acylations using acid anhydrides, is that you get a carboxylic acid byproduct, which is of course preferable to using an acyl chloride, which would of course give you hydrogen chloride as a byproduct, incredibly corrosive and difficult to get rid of safely, whereas in this case ethanoic acid is very straightforward to deal with. Okay, so let's look at each stage of our preparation of aspirin, and as we do that, I will pick out the key safety points, and I will also sort of explain the rationale for carrying out each step in the way that it is described. Okay, so we're going to start our synthesis by adding 2 grams of 2-hydroxybenzoic acid to our pear-shaped flask, and to that we're also going to add 4 centimeters cubed of ethanoic anhydride. So we're using an appropriate sort of reaction vessel. In this instance, we're using a pear-shaped flask, and so we're then going to add to that mixture a few drops of phosphoric acid. In this instance, you've got 5 drops of phosphoric acid, so a catalytic amount of phosphoric acid, and we're going to swirl the mixture to make sure it's all uniformly mixed. Okay, so whenever you add different substances to a flask, you want to ensure that there is a uniform mixture to aid quick reaction. Okay, so once you've done that, you're going to fit the flask with a reflux condenser. So that's a key piece, a key technique that you should know and be able to describe accurately in organic synthesis, refluxing a reaction mixture. So we're going to look at that next. So we're going to fit the flask with a reflux condenser. So let's move across and look at the diagram of our reflux condenser. Okay, so here I've got a round bottom flask rather than a pear-shaped flask, but that doesn't matter at all. The two are used interchangeably. So we've got a round bottom flask containing our reaction mixture. That reaction mixture, of course, contains our ethanoic anhydride and our 2-hydroxy benzoic acid and a few drops of our phosphoric acid. So what's going to happen to the contents of this flask? We're going to reflux the mixture. So the refluxing mixture is in that round bottom flask, and what's going to happen in the reflux is that your vapors are going to rise up into your condenser. So everything in the flask will be heated to boiling, and the vapors are going to rise up your condenser where they will be cooled, and then the contents or the condensed vapors of the liquid will drop back into our round bottom flask in this case. And this happens repeatedly over and over again, cycles of boiling and condensing until all of our reactants have reacted. Okay, now as with any reflux, you will need to have your Liebig condenser inserted vertically like that, and as usual, water will need to go in lower than it exits your condenser. Now, the reason for that is because you don't want to have any air bubbles forming in the jacket of your condenser, which of course then stops efficient condensation. Okay, so you want to make sure water goes in at the bottom and out at the top. Now, another important thing to note about our condenser is that it is open at the top. You should never reflux a closed system. If you're boiling the content of that round bottom flask and you've got vapors forming and you've got a sealed condenser, the pressure will build up and your apparatus will explode. So at no point do we need to have a bung or a stopper there, nor do we need a thermometer. If you're refluxing something, you don't care about what temperature the mixture is boiling at. You just want that mixture to boil, the vapors to rise up into the condenser and then be condensed back to liquid and into your flask. Okay, so under no circumstances should you have that end of our reflux condenser sealed. Okay, so that's a quick review of how to set up a reflux condenser. So in this experiment, where the reaction mixture is boiled and vapors condense back into the mixture repeatedly to ensure that acylation, which is what we're trying to do here, is completed. Okay, so back to our procedure. So we have refluxed and heated the mixture. And it says to heat the mixture in a boiling water bath. Now you can use a boiling water bath or you can use a heating mantle. The important thing is that you don't want any naked flames around, because some of our reactants, often in organic synthesis, we've got very flammable reactants, and so you don't want any naked flames around to ignite any vapors. Okay, so using a boiling water bath or heating mantle is what you want to do. Okay, so we're going to do that for 5 minutes, and then without cooling the mixture, we're going to carefully add 2 centimeters cubed. You're going to carefully add 2 centimeters cubed of water in one portion down the condenser. So we'll talk about what that water is doing shortly, but here's what we mean. So you've got the that end of your condenser open, and that allows you to actually add liquids to your flask down that to the middle of a condenser. Okay, so you're going to be adding 2 centimeters cubed of water down here, and what you're doing in adding your 2 centimeters cubed of water is you're actually hydrolyzing any excess ethanoic anhydride. Okay, so perhaps important to annotate this point. So hydrolyzing excess ethanoic anhydride. Okay, so that gets rid of any excess ethanoic anhydride. It would get, of course, hydrolyzed to ethanoic acid. So once that reaction is over, so it's when the vigorous reaction has ended, you want to pour the mixture into 40 centimeters cubed of cold water in a beaker. Okay, so we've got as far as trying to precipitate our solid. Okay, so pour the mixture into cold water. Okay, so why are we doing that? Well, we've got aspirin here, which is, of course, our product. And aspirin is insoluble in water. In fact, most organic compounds that have a substituted benzene ring, such as we've got in aspirin, will be crystalline. And they will be crystalline solids that will not dissolve in water. So that benzene ring is quite hydrophobic, and if you've got lots of benzene rings present, then you're going to have a very non-polar sort of solid, which will precipitate out of water. Okay, so the reaction mixture is going to be added to our water to cause the solid product to crash out. Okay, so what we've got here is our crystalline solid. So it says you may need to scratch the inside of your beaker with a stirring rod to make the to allow the solid to crystallize out. Now, the solid produced at this stage is not pure. Okay, so it's unlikely to be very crystalline, but we will deal with that in the next stage. Okay, so it says to allow the mixture to stand in an ice bath to complete crystallization. And then we now need to separate our solid, our product that we want, from the contents of the mixture and then from whatever else is dissolved in our solution. So remember, you've got some ethanoic acid as byproduct. You've also got some catalytic phosphoric acid dissolved in that aqueous mixture. It may be the case that you've got some unreacted 2-hydroxybenzoic acid present as well. So hopefully all that stuff will be in solution and your solid organic product can be filtered out. Okay, so we're moving on to the separation step next. And what does that involve? So let's zoom in on that section of our screen. And the separation is going to involve separation under suction using a Buchner funnel. So our Buchner funnel is this funnel here, and you can see there it's got perforations in the middle of the funnel itself. So that's a Buchner funnel. And what you're going to do is place a piece of filter paper in your Buchner funnel. So if we perhaps use a different color to indicate a piece of filter paper. Okay, so we've got a piece of filter paper and we're going to mix or swirl the contents of our beaker, so our solid and the solution that it's precipitated out of. We're going to swirl the mixture and we're going to pour that down our Buchner funnel. Now that Buchner funnel is inserted into a conical flask with a side arm, and that side arm is connected to a vacuum pump. So okay, so a vacuum pump, which could be a diaphragm, a simple diaphragm pump, which sort of works using an electric motor, or it could be a water pump, which is sort of very low tech, but works just as well. The important thing is that you've got suction, so that your solution and any liquids are sucked through our filter paper into our conical flask very, very quickly and very efficiently. Okay, so that is filtration under suction using a Buchner funnel. So if we look at the notes to go with that diagram, it says collection by suction filtration followed by washing with water. Now, the solid is going to be washed with cold water. So you've got your solid filtered onto your filter paper. And what we want to do at this stage is to wash any soluble impurities off our product. Okay, so you'll then use a wash bottle and squirt the solid on your filter paper with water, or with pour cold water over it. You want to use you want to wash it with water because your solid is insoluble in water, but you want soluble impurities to be dissolved and to be removed from that solid. Okay, so that's what you need to do. Now, even if you're using cold water, a very small amount of your solid may well dissolve in your in the washing process, and that's one area where yield can be lowered. There's nothing you can do about it. It's just that the process means that you're not going to get 100% yield. So if we highlight that point, it says note that a small amount of solid will dissolve during washing, and that reduces the yield. So that is hopefully something that you are aware of and can recall when being asked to explain why you don't get 100% yield, for example. Okay, so that's our solid separated from the contents of our reaction mixture. And the next thing to do is, of course, to purify that solid. And purification of any solid involves recrystallization. Okay, so we're going to need to recrystallize our solid. And if we look at what's required in the purification stage, there are some general principles for recrystallizing any organic solid. And these are that your solid must be dissolved in the minimum amount of hot solvent required to dissolve it. Okay, so first of all, your solid can't dissolve in the cold solvent, otherwise you're not going to be able to form crystals. Okay, so you want to find a solvent that your solid only dissolves in when very hot. So again, very hot solvent and the minimum amount of hot solvent. Okay, so once you've dissolved your solid in the minimum amount of hot solvent so that you're sure that it is saturated, you can then leave it to cool down to room temperature, and at that point you should have crystals formed which you can then filter off. Okay, if you don't have crystals formed when it cools down to room temperature, then you don't have a saturated solution, or it might be the case that you need to titrate or scratch the insides of your flask to allow crystals to form around sort of any sort of tiny shards of glass which act as nucleation points for crystallization. Okay, so let's look at our purification then in a bit more detail. So we're going to use a measuring cylinder and measure out 15 centimeters cube of ethanol into a boiling tube. So we are recrystallizing our aspirin from ethanol. Right? So 15 centimeters cube of ethanol in a boiling tube. And you're going to prepare a beaker half filled with hot water from a kettle at a temperature of approximately 75 degrees Celsius. So note the temperature being used, and note that we're not using a naked flame to warm our ethanol. Ethanol is of course very flammable, and so you want to use a hot water bath to raise the temperature of our ethanol. Okay, so we're using half-filled hot water from the kettle to about 75 degrees C, and then you're going to add your crude aspirin, your solid, to this to your solvent, to your hot ethanol. Now, in this instance, in this procedure, someone has already taken the trouble of working out what the minimum volume of ethanol required to dissolve our solid, our crude solid is. But normally you would have to do things the other way around. Have your solid and add hot solvent to it, sort of in small amounts, maybe a centimeter cube at a time, until you've got your solid dissolved. Because you don't want to start off with, say, 20 centimeters cube of hot solvent, put your solid in there and sort of cool it down and realize that you're not getting any crystals because you have too much solvent to start with. Okay, so that's something to bear in mind. So you're going to add your solid to your hot solvent. And then when you've done that, you're going to stir the contents of the boiling tube until all of the aspirin has dissolved. So we're looking at this point here. And then you're going to, once all of your aspirin has dissolved in the hot solvent, you want to then filter that by gravity. So just fluted filter paper and filtering hot, so that if there are any impurities present that are insoluble, they will be filtered out. So we're filtering hot to get rid of insoluble impurities. So any bits of sort of, who knows, grit, perhaps. Don't know how that would get in there, but any insoluble impurities, when filtered hot, will remain on your filter paper. So now you've got your solution and you're ready to leave it to cool. You're going to leave it to cool slowly, and you should get your crystals of aspirin forming. Okay, so as far as purification and recrystallization goes, what we want to do is recrystallize from the minimum volume of hot solvent. That is very important. Use the minimum volume of hot solvent. We also then want to filter hot to get rid of any insoluble impurities. So as I gave an example there, grit perhaps. And then we want to cool slowly to room temperature. Very important. The slower you cool down to room temperature, the better quality crystals you get. Okay, so you don't want to stick your hot solution into an ice bath to cool things a bit faster, because what you then get is sort of poorer quality crystals. And then once you've got your crystals formed, so it's cooled down to room temperature, you've got lots of crystals. What you then want to do is to filter your mixture to get your solid product. Okay, so again, suction filtration, so using a Buchner funnel. And at this stage, it's another point to make at this stage is that you will inevitably have some of your solid remaining in solution. Not all the solid product will recrystallize out of solution. So that's another point where yield is lowered. Okay, so recrystallization leads to a lowering of the yield. Okay, so some of your solid will remain dissolved. Once you've separated your solid by suction filtration, you will need to wash it with very cold solvent to get rid of any soluble impurities. So my final penultimate step is to wash your recrystallized solid with cold solvent to make sure that you get rid of any soluble impurities this time. And then when you've done that, you want to dry your solid. So drying your solid typically involves putting your solid on a piece of filter paper and using a second piece of filter paper, dabbing a second piece of filter paper on your solid to absorb any solvent or any liquids present. Now, you may also then to transfer that solid into a drying oven. A drying oven typically has a vacuum and is then set to a temperature well below the melting point of your solid, or well below a temperature that would decompose your solid. And you've also got a vacuum line to the oven, so that any vapors that are from solvent or water maybe gets sucked out of the oven. And that's a fairly sort of high-tech piece of kit for a school lab, so you're unlikely to see a vacuum oven in a school lab. Typically, you'd leave your solid in the fume cupboard over a few days to dry, but it's important that your solid is dry if you're going to get an accurate enough melting point. Okay, so that's the synthesis of and purification of aspirin. Okay, so if there are any questions, I'm going to pause for a second and sort of quickly have a look at my my YouTube screen to see if there are any questions. There aren't at the minute, so I will continue to look at the next organic solid that you might encounter. That the second one that we will be looking at, the second and last we will be looking at in this session. and that is, of course, the nitration of methyl benzoate. Okay, so we're all familiar with the nitration of benzene and how to make the nitrating mixture or produce the nitronium ion, which is our electrophile. So a very quick review of that. So we've got, in this instance, we've got our methyl benzoate. So it is a methyl ester of benzoic acid. So benzoic acid would, of course, be that bit there with an OH, it's the methyl group. There's your methyl group there. The methyl benzoate is going to be nitrated. And how does that happen? Well, the overall reaction is reacting with nitric acid, concentrated nitric acid, to give us this nitro group. We'll talk about why it's at that position, and water as a byproduct. So how is the nitrating mixture made? Because you do need to make the nitrating mixture, which produces the electrophile, before your methyl benzoate can then react with it. So you're going to need concentrated nitric acid. And again, if you're using concentrated acid, you need to think about how corrosive it is, and therefore what appropriate safety measures you need to take, such as wearing gloves, working in the fume cupboard, and using small volumes at a time. Okay, so all of these need to be borne in mind. You're going to be using concentrated sulfuric acid, so an even stronger acid, and in concentrated form, same measures need to be taken for safety. Now, mixing the two together produces your sulfuric acid protonates your nitric acid to give you this cationic species and the hydrogen sulfate ion, and then your H2NO3 plus decomposes to give you your nitronium ion. So your nitronium ion is your NO2 plus ion, and that, of course, is going to be reacting with the pi electrons in your methyl benzoate. Okay, so your H2NO3 plus breaks down to give you NO2 plus and water as a byproduct, and that's where water comes into the overall equation. Okay, so let's look at how to go about nitrating our methyl benzoate then. So first thing to point out is that your methyl benzoate is going to be dissolved in some concentrated sulfuric acid. Okay, and this needs to be done carefully. So the liquid has to be your methyl benzoate, which is solid, has to be dissolved in your concentrated sulfuric acid. You need to make sure you're doing this in the fume cupboard and making sure that you've got gloves on. Once you've done this, you then want to cool the resulting solution. Okay, so you want to cool the mixture in ice, and we'll see why that is necessary very shortly. Okay, so we've prepared our solution of methyl benzoate in our concentrated sulfuric acid. The next thing we want to do is to look at how to make the nitrating mixture. And it says here you're going to prepare it by adding drop by drop 2 centimeters cubed of your acid, concentrated sulfuric acid, to 2 centimeters cubed of nitric acid. It is incredibly important that you do this dropwise because it is a very exothermic process, and you want to control the time over which that heat energy is released. Okay, so it is critical that this is done dropwise, and you want to cool this mixture in ice as well. Okay, so cooling the mixture in ice is incredibly important. Very exothermic. Addition of the sulfuric acid to the nitric acid has to be done 1 drop at a time. It has to be done slowly. Very exothermic process. Very corrosive substances. So you do need to be quite careful about that. Okay, so let's look at. So having prepared our nitrating mixture, we now want to look at what happens next. So how do we add our nitrating mixture to our methyl benzoate? Okay, so now we're going to add the nitrating mixture drop by drop again. Okay, so very carefully doing so drop by drop from a dropping pipette to the solution. And again, it's a very exothermic process, So you want to make sure that you're controlling the release of heat energy. The other thing to point out is that we want to make sure that you don't get multiple substitutions. In other words, we only have one nitro group being added at the 3 position and not 2 nitro groups at the 3 and 5 positions. And cooling this at room temperature allows this to happen. Okay, so not room temperature, I should say. So below 10 degrees Celsius means that we can control the nitration to just the 1 position. Okay, so drop by drop from a dropping pipette to your solution of methyl benzoate, and then you're going to stir the mixture with a thermometer and keep the temperature below 10 degrees Celsius. Okay, so when the addition is complete, allow the mixture to stand at room temperature for 15 minutes. So that allows it to, at that point, you can then precipitate your solid by pouring the mixture into 25 grams of crushed ice. So we're going to crystallize or get crystals of our product, our crude product, by pouring the reaction mixture into crushed ice, allowing all of that ice to melt, and then filtering your crude solid. Okay, so at this stage, you're going to then go about doing a suction filtration, just as you did for aspirin, and then you're going to then recrystallize the solid in the same way as you did for aspirin. Okay, so in terms of the separation and purification of the organic solid, the processes are very similar for the different solids that you would be synthesizing. Okay, so now is a good point to check to see if there are any questions on YouTube. There are at the minute. Let's have a quick look. Okay, so there are no questions on YouTube, and there are no questions on Zoom either. So what we will do is quickly review the process of checking the purity of your organic solid. So once you've recrystallized it and dried it, how are you going to confirm the purity of your organic solid? And that technique, of course, involves taking the melting point. Okay, so how do we take the melting point of an organic solid? The first thing we need to do is to ensure that we've got a very dry sample. If you don't have a dry sample, you effectively have impurities in the form of solvent. So it could be water, it could be whatever solvent you've crystallized it from, say ethanol perhaps, and that will have the effect of lowering the melting point, and also will have the effect of your solid melting over a range. Whereas if it was very pure, there would be a sharp melting point. So that's an important point to make. So pure solids have sharp melting points. And impure solids melt over a range of temperatures and lower than so impure solids will melt over a range, so perhaps 145 to 150 degrees Celsius instead of 148, sort of bang on. And they will also sort of melt at a temperature that is lower than the reported melting point in your data book. Okay, so let's look at the two pieces of apparatus on our screens to see how these sort of can be used to measure the melting point of our solid. So the first one on the left is what is known as a Thiel tube. I'm going to zoom in on that. So this is a Thiel tube, and it might look as if it is it is a completely sealed system, but in fact the notched, if we use a highlighter perhaps to point that out for you, so there is a notch in the bung. So there's a notched cork holds the thermometer without pressure building up. So there is a gap in there to allow the release of any pressure. So we don't want any pressure building up because it would be obviously liable to explode or break apart catastrophically. So what is a field tube? So it's got oil in the tube itself, which is being heated at this point, and you can see that you've got the oil circulated round. Hot oil rises, and then where it cools down, it drops back down. So you've got this cyclic flow of heated oil, and you've got a thermometer attached or inserted into your field tube, and to that thermometer you've also got your capillary tube containing your, we use a thinner highlighter perhaps, we've got a capillary tube which we've got highlighted in green here, and that is strapped to your thermometer, and that will therefore the temperature of the thermometer would agree very closely with the temperature of the solid in that capillary tube. Okay, so it simply becomes a case of observing at what point your solid in that capillary tube that is strapped to your thermometer, at what point it melts, and noting the starting sort of melting temperature and the final melting temperature, which will typically be over a very short range, depending on how pure your solid is. Obviously, a very pure solid would melt at a very fixed, a very sharp temperature, whereas if it is impure, you're likely to have a melt over a range, a short range of temperatures. So that is your field tube, and the apparatus to the right is a slightly more modern version of a melting point apparatus. And this time round, there are no heated liquids or oils. What you've got instead is a heating block, a steel block with holes in it into which you can insert your capillary tube. So I'll annotate that. So the steel block with holes, the capillary tube, or melting point tube. So melting point tubes are essentially a capillary tube with one end sealed off, and then you can put your small amount of solid in and insert it into that steel block, which then gets heated very, which can then be heated very accurately. And there is a digital sort of readout of your temperature. Okay, so that digital readout tells you what temperature your steel block is at, and then up here is your viewer, your eyepiece for viewing your sample, a bit like a microscope. Okay, so we're going to be looking down that eyepiece at your sample, which is inserted into that block of steel to melt it, and you're going to be paying attention to when it starts melting, and then noting what temperature it starts melting at and what temperature your sample is finished melting at. Now, typically, we're talking about sort of 2 or 3 millimeters depth of sample in your melting point tube. Okay, so that's your melting point apparatus, a digital version of the melting point apparatus. Now, another thing that is important when taking melting points is to ensure that as you approach the melting point, if the melting point is known for a substance that is known, that you want to slow down the rate of heating. Okay, so it is important that you slow down the rate of heating and that should have that should allow you to get a more accurate measure of the melting point. Okay, so testing for purity of an organic solid requires you to measure your melting point accurately. Okay, so now that brings us to the I guess the end of the part of our session looking at actual sort of practical technique. In the final 20 minutes or so, we're going to look at some questions based on practical chemistry and questions based on the synthesis of an organic solid. I have had a quick look at my Zoom chat box. There are no questions. There are no questions on YouTube either, so we will plow ahead with tackling some exam questions. Okay, so the first one looks at the synthesis of another analgesic. So not aspirin this time, but we're looking at paracetamol. Paracetamol is formed by, first of all, reducing the nitro group of our nitrophenol to an amine. So we're looking at that nitro group, and then that amine is then acylated to, so here's your acyl chloride or ethanoyl chloride in this case. That amine is acylated to give you the amide. So we're looking at paracetamol, and we've got quite a nice question here. We're going to do it in its entirety because I think it's useful to look at the calculation as well. It's a bit of useful practice. And in this calculation, or rather in this question, we're asked to, we're told it describes a two-stage synthesis. We're asked to describe a two-stage synthesis of 5 grams of pure paracetamol. So 5 grams of pure paracetamol from 4 nitrophenol. The overall percentage yield of paracetamol from 4 nitrophenol is 40%. Okay, now in our answer, we need to include the mass of 4 nitrophenol that's going to be required, the reagents and intermediate, and details of the purification of paracetamol. Okay, so 6 marks, quite a bit to do. Describe a two-stage synthesis of 5 grams of pure paracetamol. Okay, so let's have a go at doing it then. The first thing to do, I guess, is to work out how much of our 4-nitrophenol is going to be needed. In order to do that, we will need to work out what the molecular formula of paracetamol is, to work out how many moles of paracetamol we're making. Okay, so let's look at the molecular formula. There are 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we've got paracetamol and its formula being C8. How many hydrogens? We've got 1, 2. Let's make this a bit more systematic and use a different color. So hydrogens are starting with 1, and then we've got 2, 3, 4, 5, 6, plus another 3, so we've got 7, 8, 9. Okay, so there are 9 hydrogens, H9, and we've got 2 oxygens, and we've got 1 nitrogen. Okay, so that is our molecular formula for paracetamol, and we can work out what the MR for paracetamol is. And so that would be, need to use our trusty calculator, so we would look at 12 times 8, which is 96, and then 96 plus 9 is 105, and then 32, 137, plus 14, which gives us 151. So we've got the MR of paracetamol being 151. Okay, so 5 grams of pure paracetamol. So 5 grams represents 40% yield. Okay, so 5 grams is equal to 40% yield. 100% yield would therefore be 100 times 5 over 40. So we're looking at okay, so we've got 50 over 4, which would be, let's have a quick look, 12.5 grams. Okay, so 100% yield would be 12.5 grams. Now, if we work out how many moles 12.5 grams is, 12.5 grams divided by 151. 0.0827, or 828, I should say. Let's just double check that calculation. 12.5 divided by 151. Okay, so 0.0828 moles if we had 100% yield. Okay, so we would be looking at starting off with 0.0828 moles of 4-nitrophenol. Okay, so we need to work out the molecular formula of 4-nitrophenol. 4-nitrophenol is, we've got 1, 2, 3, 4, 5, 6. This is C6. And we've got hydrogens. We've got 1, 2, 3, 4, 5 hydrogens. And we've got 3 oxygens this time round. And we've still got 1 nitrogen. Okay, so MR for 4-nitrophenol is equal to 12 by 6, which is 72. And add to that 5 from the hydrogens. And add to that, we're going to have 48 from the oxygens. And add to that, we're going to have 14 from the nitrogen, which is 139. Okay, so 139 is the MR for 4-nitrophenol. And now we can work out the mass of 4-nitrophenol. The mass would be equal to 139 times 0.0828, which would be equal to 11.5 grams. Okay, so we would need to use 11.5 grams of 4-nitrophenol to get our 5 grams of pure paracetamol at 40% yield. So that is an important calculation you would need to do before you actually carried out the experiment. Now, so what we've done is worked out the mass of 4-nitrophenol required, so we've just done that bit. We now need to look at the reagents and intermediate formed. So as far as the intermediate goes, we would need to make our amine. So we would need to go from our nitro group, NO2, and OH here. We would need to react that with reducing agent. So in this case, tin and hydrochloric acid would be what's required to give us our amine intermediate. Okay, so that is our amine intermediate being formed, and details of the purification of paracetamol. So we would need to recrystallize paracetamol, so recrystallization. We need to go into a bit more detail. We can't just say recrystallization and leave it at that. So we would need to dissolve paracetamol in minimum amount of hot solvent. Dissolve in minimum volume of hot solvent. Leave to cool. room temperature. You might want to titrate or scratch the inside of your flask. Form crystals. You want to then filter crystals under suction. So using a Buchner funnel, wash crystals with cold solvent. Dry your crystals. So dry your crystals in a drying oven, or just leaving to air dry. So that would be how you would purify your paracetamol. Okay, so that is quite a good sort of practical question on synthesis of an organic solid, a bit of calculation to work out how much reactant you would need to make a certain amount of your product, and then going ahead and carrying out the reaction itself. So very good practice there. Let's have another question. So this time round, we're back looking at aspirin, and we're told that salicylic acid can be used to make aspirin. Before using a sample of salicylic acid to make aspirin, the student purified the acid by recrystallization. So we're purifying the starting material, our salicylic acid. And the method for recrystallization is outlined below. So the sample is dissolved in a minimum amount of hot water. So the solvent is water in this case. We've got hot water there. And then the solution is filtered hot. And the filtrate is cooled in ice. And then the crystals are collected by filtration and washed with cold water. Explain the purpose of each underlined point. This is something that you would be required to do in an exam, to actually say why a step is carried out. So the minimum volume of hot water, the minimum volume ensures that you have a saturated solution. So ensures a saturated solution is formed. Okay, and hot water to make sure that your solid dissolves. So if you're going to purify an organic solid, you need to, by recrystallization, you need to make sure that all of your solid dissolves, and then it is recovered by recrystallization. So the crystals forming out of solution would be pure without any impurities mixed in. Okay, filtered hot ensures that any insoluble impurities are removed. Okay, so the filtrate is cooled in ice to form crystals. So cooled in ice, so that allows a maximum amount of pure solid to recrystallize. Okay, so if you leave your solution to cool down to room temperature slowly, you will get some crystals forming, obviously, but it would also mean that you've got some crystals that still remain dissolved in your solution. So that your yield is will be a bit lower than would be expected. So cooling down to room temperature slowly, and then sort of cooling further. So in a nice bath will ensure that you get sort of the most or maximize your yield of solid being recrystallized out. And then you're going to wash your product with cold water, and this will ensure that any soluble impurities are removed. Okay, so that is, these are all key points to note when it comes to recrystallization. I think we have time for at least one more question. Let's have a quick look. So this looks at the preparation of aspirin and the filtration of the crude product under reduced pressure. You'll also draw a diagram to show the apparatus you would use to filter the crude product. So we're going to have a conical flask with a side arm, and you're going to have in that conical flask, you're going to have your Buchner funnel. And in your Buchner funnel, you're going to have a piece of filter paper. And so that is the basic outline of the apparatus you need. And of course, that would be to vacuum pump. Let's label our filter paper. And Buchner funnel. Okay, so this is draw a diagram to show the apparatus you would use to filter the crude product under reduced pressure. So that's exactly what is required. It says you're provided with a small sample of pure aspirin in a melting point tube. Describe briefly how you would determine an accurate value for the melting point of aspirin. You're going to heat it in a melting point apparatus. You're going to slow down heating near melting point and record the temperature. So it should be a sharp melting point. If pure. Okay, so hopefully you found this live session sort of useful. We've looked at various techniques involved in the synthesis and purification of an organic solid. So we've looked at how to recrystallize, for instance. We've looked at how to set up an apparatus for refluxing or reaction mixture. We've looked at some of the safety precautions you need to take when working with concentrated acid and when working with mixtures, reaction mixtures that are very exothermic. So hopefully all any questions you had prior to this session have been answered. But if you still have any sort of lingering sort of questions about any of the techniques you've seen, then please do get in touch with us. Use the comment boxes underneath each live video to drop us a line, and we'll be thrilled, to get back to you with an answer. As always, it's been a pleasure hosting this live session, and I hope that you have a very pleasant rest of your weekend, and look forward to seeing you again soon. Thank you very much for joining me.